Okay, so hi everyone. I'm Ran from the Technion in Israel, and thanks for inviting me here. And I will be presenting work I did with Gil Inziger and Erez Weisbard, Roy Friedman, and Marcelo Luisielli. So first I want to mention what is network measurement. So you can think of a router, and it needs to route packets. So every time it sees a different packet going on, and it has to figure out where to send it. But while doing that, we also want to analyze the data that we're seeing. So for example, if these were the let's say the source IPs of the packets we saw, the elephant flow problem is to identify the flows which took a lot of the bandwidth or appeared a lot of the time in the stream. And if we can identify these flows, so this can be used for load balancing and caching and things like that. For example, if you want to do load balancing and you can successfully identify the flows which take a lot of the bandwidth, you can run some smart load balancing algorithm on those because you don't have a lot of them, and then just use a random allocation for the rest of the flows. And there are other problems that we might want to answer, such as counting the number of distinct elements, estimating the fraction of rare flows, and other problems. But I'm going to go into detail on one specific problem, which is called frequency estimation. So in the frequency estimation problem, we see a stream of identifiers. And these identifiers can be the source IP, maybe the entire flow identifier, maybe a source and destination pair, which can be used to create metrics like Chen used yesterday for designing the topology of the network. If you want to know how much traffic is going between each two nodes and so on. And what we want to do is, after seeing this stream of packets, we want to answer queries such as how many packets has this robot sent. And while this sounds trivial, we have a few issues with this problem. And there's a difference between what used to be the challenges, what I call in the classical setting. So if you want to make the measurement on the router itself, you have a problem that you can't allocate a counter for each of the flows. And the reason is these routers have to route hundreds of thousands, maybe a million packets each second, and the memory you think of, such as DRAM, is just not suitable for these speeds. So you have to use a memory which allows you millions of accesses per second, and this memory, such as SRAM, is a lot smaller than that. So you really have to make sure that your algorithm takes very little space, and this means that you can't allocate a counter for each flow. So you somehow need to do this with a limited space. On the other hand, if you are doing the measurement in software, right? So if you're running a virtual switch, something like that, the challenge is different. Because now memory is not as expensive anymore, so we can afford using more memory. But the bottleneck is the speed. So if we have a virtual switch running on a server, we want to consume as little as we can from the CPU and other resources of the server. Okay, so what I'm going to start with is I'm going to discuss two classical algorithms, so algorithms that were designed to save space and solve the frequency estimation problem. And then I'm going to discuss how we can accelerate algorithms. So we're going to take a black box algorithm for frequency estimation, and we are going to accelerate it at the cost of additional memory. And then I'm going to go into a problem named hierarchical heavy hitters, which is related. I'm going to see it in a bit. So the first algorithm I'm going to mention is called the counting sketch. It was by Cormod and Muthu here from Rutgers. And Muthu is from Rutgers anyways. And the idea is to take the memory that you do have and create a matrix of counters out of it. And you initialize these counters all to 0. And now you start seeing packets. So maybe the slopester arrived. And what we do now is for each of these rows, we're going to have a hash function that maps item identifiers into counters. So every element is going to be associated with a single counter at each row. So it's going to look something like that. And now when the slopester arrives, we're going to compute these hash functions and increment the relevant counters. And now if a different element arrives, so we're going to compute the hash functions for this robot. And there's going to be some overlap between the counters of different elements. But if you have enough counters in each row, there's not going to be a lot of collisions, right? So we increment the counters that correspond to this robot, and this is the way the algorithm continues. So if the slopester comes again, the hash functions are going to map into the same counters as before, so we increment the value once again. So that's the way the algorithm makes updates. And now I want to answer queries with this structure. So if you ask me how many times this slopester arrived, I can ignore everything in the matrix except for the counters which are associated with it. And what we can do is take the minimum out of all these counters, because we know that every time it arrived, it incremented all of them. And if we see here, for example, a counter which is larger than the rest, it means that it is due to a collision with another element. So every counter here is an overestimator, and so is the minimum. And this way we make sure that we can bound the error with a certain probability. And another interesting feature of this algorithm is that it is linear in the sequence of incoming packets. So for example, it supports deletions. So maybe I have an application that needs to allow some elements to be deleted, so now I can go and decrement the value of the counters. And also you can think of if you have more than one router, you can run this algorithm on each of the routers in your network, and then you can combine it simply by summing these matrices and so on. So that's the algorithm, and I'm not going to go into the details of the analysis, but what you need to think about is that what it guarantees is that the error we're going to get when querying some element is going to be larger than an epsilon fraction of the length of the string, of the number of packets we've seen, only with a small probability, right? So it has this epsilon delta guarantee, so with probability of 1 minus delta, the noise is going to be at most an epsilon fraction. Okay, so I'm going to discuss one more algorithm for this problem. It's called the space saving by Metwali et al. And the idea is as follows. Now I'm going to have a table of counters. Now each counter is going to have an ID and a value. And when we see element coming in, if we have an available counter, we can allocate it to this element. And this is the way we would operate if and is what we do when we don't have an available counter. So what space saving does is it takes a look at the table, finds the counter with the minimal value, and it now allocates it for the new element, and also it increments its value, even though it wasn't allocated for this one before it arrived. And now how do we answer queries? So if you ask about some identifier that has a counter, we can just find the value of the counter. So the answer for a query for this lobster would be 3. And if you ask for some flow that doesn't have a counter, such as this robot, which no longer has a counter, so we're going to find the minimum value, and this would be our estimation. And what this algorithm guarantees is that if we return a value, then it's always an overestimator for the true frequency of the algorithm. So we never underestimate. And our overestimation is bounded by the length of the stream over the number of counters. So if we want to provide similar guarantee to the count-min sketch, so we want to get an epsilon fraction additive approximation, so we will require 1/epsilon counters. And that is compared to 1/epsilon times log 1/delta counters in the count-min sketch. So this algorithm is usually considered better in terms of memory, but it doesn't have the nice properties such as the linearity that we discussed earlier. Okay, so now that we know some algorithms for frequency estimation, I'm going to discuss a work we did about accelerating existing algorithms. So I'm going to show it in our one slide. It's going to be very non-formal, but the idea is as follows. Every time we are going to see a packet, and I forgot to mention, but both the count-min sketch and space saving can also support weights. So it means that every time you see a packet, you can look at the size of the payload and then estimate the volume of flows rather than just count packets. So what we are going to do now is accelerate an algorithm that supports weights, and we can also support weights. And the idea is this. So assume we have a new packet coming in with an identifier of x and a weight of w. So first, we are going to keep track of the total volume of the stream, the total volume of the packets we've seen so far. And now, with a probability which is some function of the current weight divided by the total weight of the stream, and this is going to be some monotonically decreasing function I'm not going to go into here. But conceptually, the larger W is, the larger the packet is, the more likely you are to follow this path, and the longer the stream, the higher volume we saw so far, the lower probability you're going to follow this path. And what you do if you chose to follow this path, so you're going to take a measurement algorithm, such as the count-min sketch or space saving we discussed earlier, and we are going to add this element x to this algorithm, but we are going to scale its weight by 1 over the sampling probability. Right, so if I sample it with a probability 1/4, so I'm going to add it with 4 times the weight it came with. And on the other hand, if I don't follow this path and I don't update the algorithm, I simply ignore the packet. Right, so that's the idea. And what we get is that if we started with a stream with n packets and some epsilon delta algorithm, such as the count-min sketch or space saving, what we get after applying this sampling scheme is a stream with only a logarithmic number of packets. So we are only going to add to the measurement algorithm logarithmic number of packets times some factors in epsilon and delta. And in return, we are going to we have doubled the error and tripled the error probability, right? So if you have more space, so you can make sure that this fits your needs, and then you can ignore most of the stream and only perform updates for small portions of the stream. Yes?
Shouldn't it be that epsilon related to the number of unique elements you observe and not the length of the string?
No. So this is this analysis holds for any input distribution, and it doesn't matter how many times each element arrived. So as long as the total size of the stream is n, you're going to get this guarantee.
But can't you get a better result if you know how many unique elements?
If you make assumptions, yes. If you make assumptions on the input distribution, so you can either get a better error guarantee here, or you can further reduce the sampling probability and get higher speed up. Okay. And what's interesting is that now we can take this algorithm and apply it recursively. So we can iteratively accelerate ourselves. We haven't really tried it because you would need a huge trace for it to make sense, because we already got like a logarithmic number of packets. But in theory, we can repeat this process and accelerate ourselves further. Okay, so let's look at what this does to existing algorithms. So you have here the count-min sketch I mentioned. You have here two implementations of space saving. One of them only supports unweighted updates, but it runs in constant time, so it's a bit faster. And the other one is a heap-based implementation, which is a bit slower. And what you can see is that the x-axis here is the number of packets, like the length of the stream. And what we get is that the longer the stream is, the lower probability we can use for the sampling process, and the more speed up we get. And on the other hand, if we look at the effects of the desired accuracy guarantee, so if you allow large errors, so we can sample almost all of the packets, and then we get great speed up. But if you insist on very small errors, so we pretty much have to update each and every packet, so we converge to the existing algorithms. Okay, and one more thing is now we can also look at the error of the algorithms. So I discussed what happens in theory. So in theory, we double the error and triple the error probability. But in practice, and this evaluation was done on a real backbone trace from Qaeda, we see that the algorithm's performance is pretty much the same, both when looking at the length of the stream and when looking at the desired accuracy guarantee. And I want to mention here that this was done for using the same number of counters for the accelerated and unaccelerated version. So in theory, we should have allocated twice as many counters to get the same error guarantee. But here we use the same number of counters, and we see that the performance is almost the same. Yes?
So in which order are you choosing the pockets, like in the algorithm that you just said? Is it with this probability we're adding which element to this pocket, and otherwise you just ignore it and go to another, right? So I think that the ordering matters, right?
So our algorithm doesn't assume anything about the order, so the order can be adversarial.
The order of pockets.
Well, we don't assume anything about the order of packets.
So randomly, so you just when you start from.
It can be adversarial. Okay. One more thing is that we wanted to show that this acceleration schemes actually helps us. So we took an existing distribution of a virtual switch, of Open vSwitch, and we had this path where data comes to the switch, goes to one VM, comes back to the switch, goes to another VM, and then we have our algorithm here. It's called Skipper, and we can either perform the measurement inside the data plane or send it to a dedicated VM that does the measurement. And then we also need to route the packets elsewhere. And what we saw is that compared to the vanilla OVS distribution that doesn't do any measurement at all, by paying about 4% in the throughput of the switch, we can use this accelerated version of space saving. And on the other hand, if you look at the existing implementation of space saving, you would pay a much larger overhead. So it's like 20% on top of our overheads. And we got similar results for implementing it in a different VM. So now I'm going to go into one more problem, which is called the hierarchical heavy hitters problem. And in this problem, we're going to have this nice guy here. And he has access to a network of devices. And we assume that these devices come from either a single network or a small number of networks. And now he used these devices to access our server. And the question is, like, if we find that this is not a legitimate request pattern, can we block only the devices that are attacking our server? And the answer is, in general, we can't. But what we can do, and what this problem aims to do, is identify the smallest networks we can find that generate excessive amount of traffic. So this way, we can stop the routing for packets from these networks, but keep the service available for other customers. And there's also a concept of multi-dimensional hierarchies in which we might not have a single server, but we might have a network of servers and things like that, but it's not that important. I'm going to mention an algorithm by Mitzmacher et al. That solves this problem using the space-saving algorithm we discussed earlier. And the idea is as follows. So every time it sees, let's say, the source IP of the packet, so what they do is they compute all of the prefixes of this address, and each of them is going to be measured in a different space-saving instance. So this allows us to estimate for each network how many packets came from this network, right? And now I'm going to discuss what we propose. So we wanted to reduce the runtime of this algorithm, and the idea is as follows. So when a packet comes, I'm just going to compute one single random prefix of it and update a single space-saving instance. That's the essence of the algorithm. It makes the analysis much more complicated, but intuitively, that's all you need to know. And one more flavor of this algorithm, which I'll argue that we also need, is we can first sample packets. So let's assume that I'm going to just ignore 90% of the packets. And then the packets that were selected from the sampling phase, I'm going to compute a single random prefix for them and then update the relevant space-saving instance. So that's the algorithm. And this raises the question, now that we can estimate how many packets were sent from each network, we want to find the minimal prefix networks, right? So we don't want to block too many of our users if we can block just a small network. And I'm not going to go into this right now because our solution is quite similar to Mitzenmacher's. It requires small adaptations, but I will discuss it today at the open problem session if you're interested, because I don't think it works that well, but I don't have a better solution right now. And the other thing is, now that we are using this sampling algorithm, we need to consider how long it takes for us to converge. Okay, so what you have here is, this is our algorithm without sampling, this RHHH. And this 10 RHHH is the algorithm which first samples only 10% of the packets and then select a random prefix. And here the x-axis is the length of the stream. And the y-axis is the percentage of accuracy errors. And what you see is that when the stream is long enough, and whether you can or cannot afford waiting for this algorithm to converge depends on the number of packets going through your link. But if you can wait, let's say, 100 million packets, so the error of our algorithm is going almost to 0. And we got similar result for the other metrics used for evaluating these types of algorithms. But what's interesting is that the update speed of our algorithm is a lot faster than existing algorithms, right? Because we only do this one update, and in this variant of the algorithm, we don't do any updates with probability 90%, and done for two-dimensional hierarchy, so source and destination AP. So the existing algorithms make like 25 updates of space saving, and we make either one or one just with a 10% probability. And then we also did OVS implementation of these algorithms. And what we got is that, so this is the vanilla OVS implementation. So this is without doing any measurement. And what we show is that if you implement our algorithm with the sampling, so you can get similar throughput. We can get almost to 14 million packets per second. And the other algorithms has a huge impact on the throughput of the switch, and so is our algorithm if you don't do the sampling. And last thing we did is we, as before, we tried to see what happens if we are going to perform the measurement on a different VM rather than inside a data plane, right? So that's these two right here. So what happens is that you have our algorithm running on the data plane, and it chooses which packets to sample, and then these sample packets are sent to another VM that does the measurement. So if we were to take all of the packets and forward them to another VM, that's what would happen if you would try to run, let's say, one of these algorithms. So you can do this in a different VM, and then you don't have to care about the throughput here. But just copying all of these packets takes a large toll from the open vSwitch. And on the other hand, if you only sample 10% of the packets and forward these to a different VM, so you can get much better throughput. Okay, so that is it. And if you have any questions. Yes.
The sampling algorithm. So there is an underlying assumptions that the heavy hitters are a small fraction of the packets. Otherwise, I'm not sure. It could the sampling with this probability that you use could capture this population.
So, so usually the threshold you use for deciding this is a heavy hitter or not, for hierarchical heavy hitters, if you look at previous works, is generally like you can't have more than 1,000 maybe different hierarchical heavy hitters, because you really want to identify the networks that create excessive amount of traffic. You don't want to look at a large list of networks that doesn't allow you to infer anything from it. Okay.
I have again a question about epsilon. Is it must be a constant, or it could be depend on n, like 1 over square root n, or in all
in which algorithm?
In general, the algorithms, because is it only true the result for constant epsilon, or also non constant?
So these algorithms were designed for constant epsilon. If you want the epsilon to go down as a function of the stream length, you would need to allocate more memory as the algorithm proceeds. And I'm not saying that this is impossible, but I just don't know if anyone looked at into it. Because if you want to guarantee a fixed epsilon,
it was n multiply epsilon, so that's growing with n. If epsilon will be 1 over square root, it means that you need only square root memory, for example.
Yes, but in order to guarantee n times epsilon, you actually need 1 over epsilon space. So you can do better than that if you don't allocate more memory as the stream grows. There is a lower bound for this. What you can do is go from these algorithms which look at streams into sliding window algorithms, in which you only look at the last W elements of the stream, and then you can get an epsilon fraction of the size of the window, which is fixed, right? So this way you can guarantee that the error doesn't grow.
Any more questions? Okay, thanks, speaker again.